Well, good morning. Here we are. I want to talk to you a little bit about equilibrium worksheet number 6, Le Chatelier's principle. The last video podcast, I think I taught you the ideas, and that's nice to listen along to the notes, but it really isn't the same thing in my mind as practicing what you may have learned or what you think you learned. At the last video podcast, I had asked you go ahead and start this worksheet, and what I want to do now is try something that I've kind of called a living answer key. It's one thing to get something in paper format, but what I would like to do is try to walk you through how some of these things work. Okay, so that's our focus for today. Hopefully you should have done this already, and I would also recommend that you start and stop with each problem to make sure that you're really getting it. Certainly come in if you have questions after this. As we first take a look at equilibrium worksheet number 6, Le Chatelier's principle, we really want to view this as an easy idea, and when you've done enough practice you understand how the game is played. The first thing that we want to do is when we look at problem number 1, I think the hardest problems on here are problems 1 and 2. Will the equilibrium shift to the right or the left when the temperature is increased? Well, we know if we increase the temperature, we increase the heat, and that would certainly cause the equilibrium to shift to the right. Okay? Clearly, that's the case. If we take a look, though, at a big idea so far, what happens to the value of K? Well, here's what I know. I know that K would be equal to products over reactants, and the coefficients do matter. Okay? And what we're talking about here is if the temperature is increased, what we talked about in part A, if the temperature is increased, okay, clearly that's going to go up, it'll shift to the right. And what we mean by that is that this is going to go down by x, up by 2x. So it's definitely shifting to the right. A big idea that you'll hear over and over and over would be that K, the K value, is tied to a temperature. And so you've seen in problems where I'll say K is equal to 54.3 at such and such a degree Celsius or Kelvin. The K value changes with changing temperature. So it's important that we recognize the only way to change a K value is to change the temperature. Otherwise we would say it shifts left, shifts right, but does not change the K value. Temperature changes affect the K value. So I look at this, and if it's going to go to the right, then what that tells me is that the numerator gets bigger, okay, and the denominator is going to get smaller. And anytime that happens, if we just think mathematically about something such as that, what we're going to see is that the K would be expected to increase. Okay? The K value will increase because, again, as I'm saying here, the denominator gets larger. Or excuse me, the numerator gets larger, the denominator gets smaller. And that type of a change is going to cause the K value to go up. If we then slide on down to the second one, let me get rid of this. In problem number 2, what we're talking about there, same idea applies, except now we have heat on the right side. And if heat is on the right side, that would be an exothermic type of process. If the temperature is increased, we are adding heat energy, which would cause the equilibrium to shift to the left. So the right answer for this is it shifts to the left. Again, we then ask what happens to the K value. Well, again, I know that K is equal to products over the reactants. And what we're seeing is the with this shift up here to the left, what we see predictably is that this is going to get smaller in the numerator, and the denominator gets larger, and therefore overall what we see is that K would be expected to decrease. Now I can't emphasize enough that K is tied to a temperature. K is tied to a temperature, and the only way we touch the K value is if we change the temperature. Okay? So that's an important thing to recognize. All right, let's crank these out. I think those are the two hardest problems, to be honest with you here. Okay, erase that. All right. Problem number 3, what we're looking at, gaseous carbon dioxide. The most important thing, or what students have struggled with in the past, has been what is carbon dioxide? That's carbon dioxide. Over here, that's carbon monoxide because it only has the one oxygen. So carbon dioxide is CO2. If we remove that, okay, then that molarity goes down. The system is going to shift to the right to try to replace that. Okay? If we then consider that water vapor, now pay close attention, that's water in the gaseous form. There's a temptation to say, oh, it's H2O, so therefore it's a liquid. No, it's a gas in this problem at this particular temperature. If we add that, predictably, it would shift to the right. Okay? The last one, the addition of helium gas. That qualifies as an inert gas, and I notice that it is not listed up here in the equation at all. Helium is He, okay? He gas is not a reactant, nor is it a product, therefore it would not have any effect. No effect. Okay? So hopefully that gives you an idea as to how to look at each of these things. Problem number 4. Let me make sure we're good on that. Okay. Problem number 4. What we're looking at here is we have, let's see, some of the CO2 were removed. If that's going to be removed, the system will shift to the right, trying to replace that. Okay? Then we deal with something that I'm not sure I really talked a lot about in the notes. Okay? So here we go. We have to recognize the word solid appears. And if the word solid appears, we know that pure solids and pure liquids do not impact the equilibrium expression. Since that is a solid, I can immediately say no effect. Okay? Similarly, some of the solid, if that were removed, no effect. And in the past, students have said, oh, aren't you quite the trickster, Mr. Bracken? You didn't teach us that in the notes. You're right. However, we have talked about how pure solids and pure liquids do not appear in the equilibrium expression. Therefore, the solids are not going to play the Le Chatelier game. Okay? Now that you know that, you'll probably immediately see it and never be tricked again. Okay? If we look at problem number 5, problem number 5, it's another way of asking what I think is essentially the same thing, and that is, does it shift to the left or to the right? Since we're talking about the number of moles of SO3, anything that causes the equilibrium to shift to the left would cause an increase in the number of moles of SO3. Okay? Anything that causes that equilibrium to shift to the left would effectively increase the number of moles of SO3. Okay? So that's what we're really talking about. Does it shift to the left or to the right? And here we go. Oxygen is added. That would cause the equilibrium to shift to the left, thereby increasing number of moles of SO3. The pressure is increased by decreasing the volume. Well, if we increase the pressure, we hit the side that has more moles of gas. So I look here and I see that we have a total of, I don't know if I'm off the screen, 3 moles of gas versus 2 moles of gas. Therefore, if we increase the pressure, it's going to go to the left. If we increase the pressure by adding argon gas, no effect. And that's because argon is not a reactant, nor is it a product. It's an inert gas that we're adding. I'm looking at here and I've got a lot of clutter. Let me get rid of some of this. The temperature is decreased. That means I would be lowering the heat energy. If I do that, it's going to shift to the left, thereby increasing the number of moles. Okay. A catalyst, no effect. And it appears that our newspaper is being delivered. Shh! Katie! Sorry about that. It is 6:42 on a Sunday morning, and the newspaper... Just a moment. Okay, well, hopefully we are still recording. Katie is now done talking, apparently. Sorry about that. Part F, gaseous sulfur dioxide. Gaseous sulfur dioxide, what we're looking at here. Gaseous sulfur dioxide, that's this stuff. If we remove that, it's going to shift it to the right, thereby decreasing the number of moles of SO3. Okay? Number 6, and by this point we really want to be thinking in terms of, I have this Le Chatelier thing figured out, right? By number 6, I would expect 100% success because you know how to think about these things. Practice, practice, practice. That's the important thing here. If H2 is added, it's going to go to the right. I2 is removed, it's going to go to the left. HI is removed, going to go to the right. Argon, no effect. Again, it's an inert gas, it's not a reactant, nor is it a product. The volume of the container is doubled. Well, doubling the volume, okay, if we think about that, it's kind of like a box here. And if we double the volume of the container, if we put gas molecules in there, if we then double the volume of the container, so it's now this size, okay? And we then eliminate, ooh, gravy, we eliminate the barrier in between. What we see here is a decrease in the pressure. And if we decrease the pressure, okay, if we decrease the pressure, that impacts the number of gas molecules. Okay? The number of gas molecules, or the pressure of the gas molecules, turns out we have 2 and we have 2. Therefore, since the moles of each gas are the same, since the moles of the gases are the same, no effect. If the temperature is increased, it's going to go to the right. Okay? All right. And if I look here for number 7, let's lock it in. Addition of carbon monoxide. Excuse me. Addition of carbon monoxide is going to cause the equilibrium to shift to the left. Addition of carbon, which I want to point out, that's a solid. If it's addition of a solid, no effect. Removal of some of the carbon, no effect. Addition of some of that, no effect. And removal of some of the gaseous arsenic, that would go to the right. Well, hopefully this living answer key has worked well for you. I do apologize that our dog Katie started to bark when the Sunday newspaper arrived, and it looks like Carbon brought a toy up. I don't know if you saw that, but I do thank you for your time, and hopefully this has been helpful for you.